So how do we train a multitask model? In other words, how do we train a single model to do multiple tasks simultaneously? So in our previous videos, we have learned how to prepare data from cityscapes for dense computer vision tasks. One task is more of a classification task, which is semantic segmentation. The other task is a regression task, which is going to be depth estimation. And we're going to train this model to do both of these tasks at the same exact time. So we have our basic imports here. We're going to go through our configs. We're going to get into this a little bit later. We're going to do a 16 image batch size and train for 150 epochs. And we're going to run on GPU. So this right here, we already know the image size, kind of cheated because this is how we prepared the data. And we're actually going to train at 1/4 resolution. And this is for a first iteration of training. Looking ahead, we're going to train again at half resolution, and we're going to fine tune once more at full resolution. It seems like pre-training on a lower resolution is an easy way to get a decent model, but you could actually improve performance by fine tuning at higher and higher resolutions. And if we wanted to go crazy, we might even explore some super resolution to get even better, but I don't have the computing power for that. So here's our transform. So here's our training transform right here. We have a 2-tensor conversion, random resize crop, color jitter, random horizontal vertical flips, a custom normalization for the input image and the depth. I have a video that covers this. I will link it in the bio. And I have, for the validation, we're going to still go down to our training resolution of 1/4 size and normalize, and our test transform is just going to be a full image at full resolution. So here's our PyTorch data loaders, and here you can see our training labels. We have 20 total, with one of them being an unlabeled category. And if you see what we actually have, here's our whole original labels, these left two columns. We have something like, bicycle, motorcycle, and in general, we have something like license plate, which belongs to a car. That's just going to be an unlabeled. All these ones that say 19, like pole group, that's going to be 19 and stuff. So we have a lot of things that are going to be in the unlabeled category to make it easier for our model to perform the segmentation. So 20 total, and here's just a helper function that helps us plot. Now here's an example of our training data. So you can see this random resize crop gives us a different portion of the image. Now this is going to be the same image every time. So you can see that the colors actually change, and now we get a flip. And you can see this color jitter has a pretty intense effect right here. So this actually helps our model learn more. It's a simple way to get quote unquote more training data off of less samples by using a different portion of each image each time. It's a very common technique. So here's our model. So our model consists of 3 parts. It consists of a MobileNet v3 backbone to encode the features, and a lightweight refined net to decode the features. And then at the very end, we have we combine them together and we create our multitask model. So I did some experimenting previously to freeze the weights of the encoder. It turns out it doesn't seem to work so well, so I decided to let them all be trained, and it doesn't really seem to have a major impact on training speed. It was always about 8 seconds per epoch on my computer. So actually it takes about 8 minutes per epoch. So I'm going to make sure. Now this is what I did previously to make sure they're frozen, but now we can see that all the weights require gradients, and that means that we are good to go, and we're going to be able to update all of these weights during training. So the original paper that we are following, and that's going to be, that is not this one, that is this one, real-time joint semantic segmentation. It uses something, and here's the architecture. It uses something called the inverse Huber loss, and the inverse Huber loss has been used in other depth estimation problems, and it seemed to work okay, but for this case, I'm actually just going to use MSE loss to make things easier, to make it easier to understand. So what the Huber loss does is at a certain point, it is a an L2 loss, or a mean squared error loss, and then it goes into a L1 loss, which is just a straight line. The inverse Huber loss is the opposite. From the lower loss values, it starts out as L1, or a straight line, and then transitions to L2 in a smooth manner. So we're going to kind of keep this out. So what this kind of does is, with the MSE loss, once we get to a certain value, you could see that it kind of dips below this inverse Huber, and this doesn't really encourage the model to learn a good depth estimation in other sense. But we're gonna just make things easier and use the MSE. We're gonna use cross entropy loss for the segmentation part, and we're gonna actually combine both loss and not use any weighting. There's a lot of other approaches that actually get very complicated. There's even a Bayesian neural networks that are used for this, and they always have some sort of weighting, but in this one we're just going to add them together. And you'll notice that the depth loss is much smaller than the segmentation loss, which means that the segmentation loss could easily overwhelm the depth loss. But it turns out we can learn them both, but it probably could be a lot more optimal. We're also going to do another thing. It's a one cycle cyclic learning rate scheduler. So we're going to use a cosine annealed scheduled learning rate, and we're going to max it out at 5 e to the negative 4. And what I typically almost always use some sort of learning rate warm up or a cyclic learning rate. So either this or cyclic ones are some of my go-tos. But I noticed, especially for bigger models and especially transformers, they don't learn at a static learning rate. If you do it at 1e negative 3 right here, it might not learn. It usually helps to start it out at a very low learning rate and then ramp it up, and then you can either leave it there or decay it down like this. So that's what we're going to do here. That's called our scheduler. We're going to track the Jacquard index, or IOU, and we have this nice average meter right here just to keep track of average metrics and losses that we want to keep track of. So this line right here, torch backend CUDDN benchmark true. So this essentially finds the optimal backend for your hardware to perform convolutions. I strongly recommend that you run this. It actually seems like it makes a difference on my computer. So here's going to be our main training loop. We're going to keep track of average metrics for validation and training, for segmentation and depth loss, the combined loss, and the IOU. So we're gonna pull from our data loader, put it on the model, forward pass right here, and we're gonna basically reshape everything, computer losses, and perform our back propagation and weight update, and make sure to step the learning rate. And we're gonna store our metrics. So we're gonna run this for 150 epochs, which I've already done. And you can see here's the output of the combined losses right here. You can see the validation loss is pretty far ahead of the training loss, but it looks like there's still probably a little bit more room for training. So this took probably, I want to say, at least 20 hours on my computer, so I'm probably not going to do any more training, and I'm probably not going to go back, but it just kind of shows. And I also, aside from running about 2 or 3 epochs a couple times to tune the learning rate, I didn't really do any hyperparameter tuning, so there's still lots of room for improvement with this approach. So here's the segmentation loss. As mentioned earlier, it greatly overrides the depth loss, so it's roughly the same. And that's actually a previous one. So right here's the segmentation loss. It's roughly the same. And here's the depth loss. You see the validation loss is fairly noisy, and then the noise kind of dies down towards the end when it converges. So here's the IOU. It looks like the IOU could have a little bit of ways to go. And so that's essentially it for the 1 quarter. And I will just say, here's a prediction for a test image, and you see the depth is pretty awful, and so is the segmentation. So we're going to go to the fine tune and see how the model did. So fine tune is nothing different. Nothing too different. The only difference we made is we only used a batch size of 1 and trained for 25 epochs. And we also did, and the second fine tune where we did 2 fine tunes, one at half size and the other at full size. And at full size, we did not use any random resize, recrop. So I have the training results from them from this 25 epochs. It looks like we had still some room to improve with this loss and with the IOU. Maybe not so much the depth, but as said, this depth loss is pretty small compared to the segmentation loss. So here's some tests, some model inference test right here. So you can see here's the ground truth and here's the prediction. And overall, this is not a bad run. So I think I do want to highlight something very important. So here's some samples. Actually, no, it's in the inference. So and actually, to keep this video from going on, I'm going to end it here and I'll restart in the next one. So I'll see you on the next one.